Okay, let's get started. I like to start each lecture just like reviewing where we are. Today we're going to be doing the second of the two C++ lectures. And I actually had a few people come to me after class last time asking questions about setting up Visual Studio and stuff. That will all be done in the next lecture on Tuesday. So I'm going to go over the complete, in detail setup process for everything that you have to do to get set up for programming in this class. So if you have any questions, I would prefer you wait for that just because I'm going to be releasing everything then. But if you do have a quick question, I don't mind answering that for you. And yep, so as you can see by the spreadsheet here, you'll have 2 full weeks to work on assignment 1. And then when assignment 1 is due, I'm going to be giving out assignment 2. And so it's kind of weird that in this class there's always an assignment that's due at some point. But I'd rather do that than just give you less time, right? So I'm just giving you as much time as possible with each assignment. Assignment 1 should take, probably a couple of days. There's one little tricky part to it. So it shouldn't take you the full 2 weeks, but still I like to give you that full time. And then again, as I said in the first class, after assignment 1 is released, I'm going to be teaching some new topics, and then those new topics will be used for assignment 2, and then after assignment 2, some new topics that'll be used for assignment 3, and so on and so on. So we'll build up our game engine toward the final version that we're going to use for our project. Okay, some people showed up. I was like, damn, we're down to 10 people already in class. I mean, I expected it to happen eventually, but not so quickly. So, did anyone have a look at the lecture video yet for Tuesday's class where I put the live coding part on the end? So, okay. Well, the live coding part is there. You don't have to have watched it yet. But if you do need a little bit of extra help with C++, I'm going to do that again with this lecture. So again, the previous time I offered the course, it was online, so I could make the lectures as long as I want. So I just tacked on like an hour of live coding at the end just for some extra help if you want it. And the same thing will happen with this class. So I'll go over the slides, but then I'll put on some live coding at the end of the lecture so that you have that if you are not sure what pointer is or pass-by value or you want some practice, you can watch that live coding. Okay, so this is the second part of the C++ programming. And after this lecture, you should have pretty much all the knowledge you need of C++ for the course. And if there's something left out, then I will explain it as we go on through the course. Like, for example, when we get into assignment 3, I think I'll talk about stuff like tuples, which we're using for part of our architecture. But that's just a minor feature. It doesn't need to be in the intro section to the course. So one of the most daunting things about C++ for new C++ programmers is the memory side of things. So there are 2 different types of memory in C++, and in fact in many different programming languages, but we're talking about C++ here today. So there's stack memory and there's heap memory. When a program is launched, the operating system gives it access to a number of areas of memory. So that depends on the operating system. It depends on the architecture of your processor and your memory. But you'll be able to use some amount of RAM within some memory address space on the computer. Now this part doesn't really matter for programming. You don't really get exposed to that unless you're doing some bit hacking stuff or memory addressing stuff. But just to let you know, when you do launch a program, the operating system says, hey, you're allowed to write here, and you're not allowed to write here. So if you do something like create a pointer that's outside this allowed addressable space, and you try and dereference that pointer, it'll give you an error. So the 2 main ways that we can the main 2 that we can manipulate are the stack memory and the heap memory, which I'll go over now. And so both stack memory and heap memory are stored in RAM, right? It's just, they're still in memory, but the difference is determined by the operating system when the program runs, and there are differences between how you allocate that memory and how you use that memory. So at a basic level, they both just store data. You can store any data type that you want in both stack memory or heap memory. We request an amount of memory from either the stack or the heap, and it gives it to us. And the way that we request that memory is different for both. But the main differences between stack memory and heap memory are The first big difference is the size of the available memory. Okay, and we'll talk about that in a bit. Also, the way that the memory is found and the way that the memory is allocated. The speed of the memory allocation, so using the stack when possible, is much faster than using the heap. The syntax, or the way that we request memory in the code, is different. So there's just a different syntax for saying, hey, I want this to be on the stack versus, hey, I want this to be on the heap. And stack memory is deallocated when it leaves scope. So if you have some code scope that's determined by your curly braces, as soon as those curly braces end, anything that you have allocated on the stack within those curly braces is going to be deallocated at the end of those curly braces. So here's some example allocations. So if you just say int value equals 5, if we just normally declare an integer, that integer is on the stack. If we say int star, and so I will get into pointers, but int star is how you allocate a pointer to an integer. Okay, so star just means pointer, and then whatever type you've allocated before the star is the type of pointer. Does anyone here has used pointers in C or C++ before? So most people, okay, good. And then the way in C++ that we allocate memory on the heap is by the new keyword. So if we say new, then that will ask the operating system to look at the heap, find a contiguous area of memory where I could allocate this int, and then return to me. So the return type of the new keyword is a pointer. And so it goes, it allocates the memory, and wherever it found the memory, it returns the pointer to that memory. And then if I want to set the value of a pointer, then I have to dereference that pointer. Okay, so if I want to set the value here, I would say star hval equals 5. Now this is a little bit annoying. That one of my really biggest gripes with C++ is the overloading of operators. And so this means that like int star hval, that star means that I'm declaring a pointer, but this star means that I'm dereferencing a pointer. Okay, so the star is used in two different things. I really wish that this was like an @ symbol or something. It would be perfect. It would be like, hey, the thing that's at this location, change its value. Yep.
So if we roll hval, it would give us the address, right?
Yes. So I'll get into that in a second. But yes, if you did not have the star there, this would try to set the pointer equal to 5. And a pointer is just a memory address. That's all it is. A pointer is an unsigned integer which stores the memory address in RAM on your machine. That's literally all a pointer is. There is nothing more to it. Here's another example of allocating an array in C++. So you would say int a5 in brackets, and that would allocate an array of size 5 on the stack. Okay? And then if you wanted to allocate that on the heap, you would say int star heap array, here, HA, equals new int 5. So if you want to have a dynamically sized array, you would have to use the heap, and you'd have to use the new keyword. And what this does is it returns the address of the first element of that array that's been allocated in memory. Okay? And then if we want to set a particular element of that array, we could say, just like any other array, HA3 equals 10. And the syntax for that I'll get into in a little bit. And I have like visual demonstrations of this as well. If I want to allocate a class, it's the exact same thing. Okay? So if I say my class C with some arguments for its constructor, then this is going to be allocated on the stack. So whatever's inside that class will be allocated on the stack. Or let's say my class is like super huge. It contains like megabytes and megabytes of data, which is too big to allocate on the heap. Then I would say my class pointer HC equals new my class args. Okay, so the new keyword is how you allocate stuff on the heap. Now, that doesn't mean that all of the stuff within this class is on the stack. For example, if in this class I have some heap allocated memory that I allocate in its constructor, then that stuff will be on the heap. But the data itself will be on the stack for the class. So the class itself is on the stack. So the stack has a predefined size. By default, it's just a couple of megabytes. It's kind of small. Okay, so if we have large amounts of data that we need to store in memory, typically we will not allocate that on the stack. It is very easy to run out of stack memory. What's it called when you run out of stack memory? A stack overflow, and you've all been to that website, right? Okay, so when you overflow the stack, that's a stack overflow. Local variables without the new keyword are allocated on the stack by default, and program and function calls and return addresses are also allocated on the stack. Okay, so we're not about to drill down into the assembly here, but just realize that like as you're calling functions, that like the way it works, there's a stack, that memory, like when you call a new function, it pushes the pointer to where you are in the program counter to the stack, then you do the function, then the function unrolls, and then it tells you where in the program counter you have to go back. So all of the stuff related to function calls, returns, all that kind of stuff, that's also on the stack. So the stack is shared between these these executable related things that you're not really aware of unless you drill down into the memory of the stack, as well as the variables of your stack, right? And you can also corrupt the stack pretty easily if you're working with pointers in a weird way, and we'll show how you could do that in a little bit. And the live coding session that I will tack on to the end of this also shows some examples of that. So the stack is also known as static memory. It is the opposite of dynamic memory because the size of anything that you put on the stack has to be known at compile time. Okay, so it's static. So all stack memory allocation sizes need to be known at the time that you compile your program. So back here, where I did this, int a5, you cannot do that with a variable, okay, which may change. You can do it with a const variable, I believe. Don't hold me to that, though. But if I put a variable name in here, like array size, this would not compile, because the value of array size may change, and that would mean that it is not known at compile time. Okay, so you can only have static allocations like this. If you did want to have like a variable name that would never change, you could use one of those preprocessor defines that we looked at last time. So you could say like define array size 100, which is like a literal find and replace in your code, and then you could do something, but that's kind of unsafe. And it's very rare that we would actually use a stack allocated array in the first place. There's some uses for it, and we'll get into that later in the course, but it's very rare that we would actually do that. Memory allocations which depend on runtime variables, so things that could change, must be heap allocated, and that's a dynamic memory size. So let's look at a visual example of this. Over here, I have an example of the stack, and I'm going to show the stack going from top to bottom. And of course, it's called the stack because it acts just like a stack data structure, which hopefully all of you know. So hands up, what is the stack data structure? Can anyone explain what that is?
First in, last out.
First in, last out. Yes. So you grow it, so you add things to the top, and then you remove things from the top. Okay, that's what a stack is, and stack memory is just like that. Whenever you put something on the stack, it goes on the top. Whenever you remove something from the stack, it comes off the top. And if you try and change that in any way, good luck getting your program to run correctly. So here's an example that we'll step through. I have a very simple main program. And a little caveat that, so one of the cool things about posting my previous lectures online on YouTube is that everyone in the world gets to criticize my lectures, right? And there are people who know a lot more about C++ than me. And apparently, what I'm about to show you is true in theory, but in practice, the compiler may do something different. And in my live coding, so I was talking to this person who commented on a YouTube video, and I was like, but when I do the live coding, I show that this is true. And then that person was like, it's like this Schrodinger's cat thing, where if you inspect the memory, it works as we're about to show. But if you don't inspect the memory, the compiler may do something completely different. okay? So this is like a theoretical way that it does work, and it's like the completely naive way of doing it, but the compilers do something a little bit faster that is not exactly this way. But if you keep this in mind about how it works, theoretically it's fine. I just want to, I don't want to say, hey, this is exactly how it works, because that's not technically true. But this is a very, very accurate and good model for theoretically what the compiler and what the program is doing. Okay, so we go to the first line of code, and whenever this little red arrow is here, that means that that line of code has just executed. Okay, if you were using a debugger with a breakpoint, if this was a breakpoint, this line would be about to execute, but in this example, it has already executed. Okay, so down here on the stack, we can see that we have allocated the value of 6. And so that value lives on the stack. Here, the next line of code is executed, and now I have a 10 just above that on the stack. Then I'm going to allocate this point. And this point is a custom class that I've created, and that point is going to store an x variable and a y variable, and that's it. Okay? And so if I allocate this point on the stack, then this, the 5 goes first, because in my data structure I have the 5, or the x value first, and then the y value. So it's the 5, and then the 4. So all of that memory is living on the stack. And in the live coding part, later on in the lecture, what I show is that if you take the address of this and subtract the size of one integer from it, you get this. Right? Which is pretty neat. You can actually go through the stack and look at the variables that are there. However, if you end up changing any of those variables via pointers, that can get a little bit tangly. So now what we're about to do is we're about to exit the scope of this function. Okay? So after we get to here, then things start being deallocated off the stack. So the first thing that gets deallocated is this point, and so that gets popped off the stack. Then the B gets popped off the stack, and the I gets popped off the stack. And so that is the order in which things go on the stack and things go off the stack. Okay, so heap memory has much more available space than the stack, right? If you are running on a 64-bit operating system, you pretty much have access to all the amount of RAM that you have on your system, right? So like Chrome definitely makes use of the heap. Right? If you ever use Chrome and had to take up like a ton of RAM, it's definitely using the heap. You allocate memory, as I said before, with the new keyword. And so you would say type star, again, indicating that it is a pointer to type. And then you give it a variable name, and then this is equal to a new type. And again, the new keyword will poll the operating system and say, hey, give me enough memory that's free in a row, meaning contiguous memory. So if type would take up a megabyte of memory, then it would have to look through your RAM in the place that this program is allowed to allocate memory for a megabyte of continuous or contiguous memory, and then it returns the pointer to the start of that contiguous block of memory, and that's what's stored here. In C, you would call malloc, memory allocation. You would call malloc if you wanted to do this. C++, though, has the new keyword. So in C, you would have to say type star var name equals malloc, and then the size of the amount of memory that you want. But here in C++, we have this convenient way of doing that. So the operating system finds a contiguous chunk of memory and returns a pointer to the beginning of that chunk of memory. This is actually very complicated and expensive. So we want to avoid memory allocation on the heap wherever possible. And then once we have that pointer, we can access the memory of that pointer whenever we want to. So let's have a look at an example here. So I'm going to have the stack growing upwards. Now I think in actuality the memory addresses of the stack actually grow from top to bottom. So it goes like from here down. But that's just a weird way of visualizing it. So it doesn't really matter like if these, if the heap technically grows from the bottom up or the stack grows from the top down, just reverse it in your mind. It doesn't really matter, it's just a visualization. So let's have a look. So over here I have the heap. And the heap, I've just labeled these as addresses. Okay? So this is address number 1, address number 2, address number 3, and so on and so forth. technically you're going to have like gigabytes of RAM, probably. And these memory addresses, if you look at them in the live coding session, these will be like huge hexadecimal numbers, right? They'll be pointing to like, I have 64 bits of addressable space. So these are actually 4-byte values, okay? Actually, 8-byte values, apologies. So 64 bits, 4 bytes, 8 bytes, geez. 64 bits, 8 bytes, which is a memory address on a 64-bit machine. So here, I'm just not putting in all of those characters just to make it a bit simpler. So let's go through our program. We are going to allocate I. That goes on the bottom of the stack, okay? Then we're going to allocate j. That 10 goes on the bottom of the stack. Now what we're going to do is we're going to say pt, so this is just point. I just wanted to fit it into one line. So that's our point data structure, which stores an x and a y. So pt star p equals new point 5, 4. So if that was allocated on the stack like last time, we get a 5 here and a 4 here. But what we asked is, please go to the heap, find that memory, and then return a pointer to it. And then that pointer is what we want to store on the stack. So here's what happens. It goes to the heap. It finds the first available space where I can get a 5 and a 4. It stores that data there. And then at the first memory address of that contiguous block of memory, that's what we store on the stack. So literally, on the stack is the integer, the unsigned integer, representing the memory address where that data is stored. Okay? Then, let's say we wanted to allocate a stack-allocated array. And so we do that, then we get the 3, then we get the 4. So that's how this works in theory. In practice, if you have a super optimized compiler, it may do something a little bit different. But if you actually go to inspect the memory, you will see that then this becomes the actual model. Now what happens when we get to the closing bracket of this block of code? Well, things start to deallocate. So the first thing that deallocates is this stack allocated array. So that gets popped off the stack. The next thing is going to be this pointer, right? Because the pointer is the thing that's on the stack. So that gets popped off. Then the j, and then the I. But look, this is still living in the heap, okay? Now, if this was our entire program, right, if this was actually a main function, that's not a gigantic deal. Yes, you have like a dangling pointer at the end, but it's 4 bytes. Who cares, right? What if this was a function that got called inside a for loop that happens every frame of your game? Right? Every single memory leak in every single game is caused by this. Okay? So if you've ever run any program and the memory usage is just going up and up and up and up and up, it's because you delete this pointer off of the stack, but you did not free the memory from the heap. Okay? So this is a memory leak. This is bad. We want to avoid this. Yes, even if it is just a one-time thing like this. So what do we have to do? Well, in C++, we have to call delete. And so we would delete this point p. So after we have called new on something, we eventually have to call delete on something. And that is the really annoying thing about non-garbage collected languages where you have to manage your own memory. But a bit later in the lecture, we're going to show you how we never actually have to deal with that in practice in code like this. So here's what actually happens when you call new. Right? So new uses malloc. This is malloc. It is a huge function. It is many functions. Because if you think about all the stuff that you're running on your computer, I have to make sure I'm not interfering with this memory, with that memory. I have to make sure it's contiguous in order to get contiguous memory. Maybe, for example, okay, maybe I would want to move around some memory to make this thing contiguous. It's insane. It probably doesn't move around memory, but you can think of a bunch of different things here. I am not going to go into this, obviously, because I don't know the details. I just found these diagrams to be hilarious, so I wanted to post them. Also, that delete that I showed here, in C, the thing that delete does is it calls the free function, and free is also similarly huge. Okay? So you might think that free would be not that big, but free actually kind of has to recursively call free on functions and stuff. Delete and allocate, or sorry, new and delete are things that we want to avoid at all costs during runtime. Down here is reallocate, so it's a little bit simpler than allocate, but if we have a pointer and we want to reallocate it to a different size, well, we know we can do some optimizations there. So for example, whenever we have an array, if we're shrinking the array, we can actually use the same pointer because we know that the data will still fit in that location, right? So all we have to do there is just chop off the end a bit and then return the same pointer. So there's some things we can do in reallocate that are a little bit optimized over allocate, but most of the time we're calling allocate and not reallocate. Okay, so the C++ memory layout is actually a little bit complicated. We're not going to go into all the details of that, but just realize that a bunch of stuff is going on the stack, okay? So we've got like some system allocated things. So like the top, the bottom, the stack grows from top down. So the top of the stack would be like, if you're running a Windows executable, it would be a bunch of things that Windows needs to know about the program. Then stuff about your environment, your argc, your argv, your variables for main, different things for the functions, different library things. It's insanely complicated, okay? It is OS and compiler specific. We don't need to know the details of this for this course, and you will probably never need to know these exact details as long as you are programming in your life. Just remember that stack is fast but limited, heap is slow but large, okay? So use the stack if you can, use the heap if you can't, but as infrequently as possible. And so yeah, here's another sort of view of what's going on. So we talked about pointers. Maybe some people need a bit of a refresher on pointers. Pointers are not easy the first time you come across them. C++ pointers are basically identical to C pointers with some additional functionality that's only available in the C++ language. But in essence, a pointer is just a memory address. That is literally it. It's just an integer. If you're ever thinking to yourself, I can't understand what this pointer is doing, it's just a memory address. It's an integer, okay? Modifying the pointer variable modifies the address that it points to. So if you directly modify that variable, you're modifying the integer, which is an address. So now that variable points to something different. To modify the value of the data that the address points to, you have to dereference it with the star operator. So because of this, using raw pointers, i.e. pointers that you have allocated yourself with new, can be very unsafe. Because if you do something with them that is not correct, your program can crash. Even worse than crashing, you could have an incorrect result if you're modifying memory than you're not supposed to. Like, I would argue that your program, you would rather it crash than modify stack memory or heap memory that it's not supposed to and then output a different result, right? Like the machine that's giving you chemotherapy for your cancer treatment, would you rather it crash and stop working or give you the wrong dosage, right? Like that has actually happened before. Maybe I'll tell that story later. Okay, so C++ pointers, here again, another example where we're not using new, but we're just using pointers. Okay, so how would we do that? Well, let's allocate a local int variable on the stack. So here, I've got my stack. This is the stack. And I'm going from top to bottom just to make things more confusing for you. But the stack actually is addressed, right? There are addresses to things on the stack. I just haven't been showing them yet. So the stack starts at 1, and we're going to go down. Now what I'm going to do is I'm just going to say int star p. And this will allocate on the stack a pointer to an integer. But one of the great things about C++ is if we do not give it a value, what value will it get? You say null? Okay, which would be what number? 0. Okay, you'd think that. Nope. it doesn't get assigned a value. It just uses whatever's in RAM. It's literally, like, it's not random because we didn't generate something random, but it's effectively random, right? And like some older games use unassigned variables as the seed for their random number generator. Because it's just whatever's in RAM. Like if you print this out, it could return any number. It's insane. I think I do that in the live coding. All right, so this is bad. Because of that, there is almost never a time in C++ where you would want to declare a variable without giving it an initial value, right? So int I equals 6, perfect. I could say int I and not give it a value, and again, this would be something random. Okay, just driving that home that uninitialized values in C++ are really, really bad because you're relying on future code to set them. Now in this code, I do set it in the next line, but I should have done all of this on one line. Okay? So what is this? We don't know. Could literally be anything. It's an undefined value. Next, what we're going to do is we're going to use the ampersand operator. So the unary, meaning one argument, ampersand operator, coming before a variable name is the address of operator. Okay? So this will give me the address of I, which is, if it's an address, it is a pointer. If this variable is an int, then what address of int gives me is a pointer to an int. Since this is a pointer to an int, then I can assign p equals the address of I, right? So I don't need to use the new keyword, because all the new keyword does is gives me something on the heap, right? It allocates memory and then returns a pointer. But things, I can still point to things that are not heap allocated. So what happens here is that now that value changes to the address of where I was allocated. Okay? Then, let's say I want to change the variable, the value of what p points to. If I said p equals 7, that would change this to a 7. Right? P equals 7, this would become a 7, not this. So if I want to change the value of the thing that this points to, that is the dereference operator. Dereference operator comes before an address or a variable that is an address or a pointer, and then it says change the value of the thing that lives at that address. So this would look up the address of P, which is 0x1. Oh, I'm right here. Then it would dereference it and change that value to a 7. Okay? Now, you can see how this would get crazy dangerous because you can just start playing with these pointer values and like, what lives up here? Or right here? Or right here? You can change those values in C++, right? What it does, I don't know. Okay. So here's another example where I have allocated, so I have already run to the completion of this program here. So I sent int star r equals new int 3. So this is heap allocated. So I asked the heap, I want space for 3 integers in my array. And down here, I get the address of where those have been allocated. Now, after this line has been called, what's in the array? Whatever was in memory, right? You'd think it'd be zeros. Nope. It's just whatever happened to be there, right? So then I say array 0 equals 5, okay? So, and then array 1 equals 10, and star r plus 2 equals 20. Okay, what I'm showing you here is what this actually does. So you have all done something like this in some programming language where you take an array and you pass in an index of that array and then you give it a value. Or you just read that value. But what is this actually doing? Here's the reason that things are 0 indexed in sane programming languages. Okay? Because what this means, array n is equivalent to taking the pointer of ARR, adding n to it, and then dereferencing that. So these are equivalent statements. They're equivalent statements. So up here, what this does is it says, take the pointer, ARR, add 0 to it, then dereference it. So if you use that in the context of setting it, then you are doing what we did right here, right? If you're taking it in the context of reading it, then you are still adding 0 to this, okay? So the address that we get is the address of the first element. So if we want the first thing in the array, you add 0. That is why things in sane programming languages are 0 indexed, okay? Now, the hilarious thing is that, okay, this is our ARR plus n. Well, addition is commutative or transitive, I can't remember. It's the same backwards and forwards. So n plus ARR would give us the same value, which is equivalent to n ARR. So in C++, it is completely valid to have the index outside the variable name. They're equivalent statements. Now, I have never seen that in actual code, but it's one of these like thought experiments that you can do if you're a psychopath, right? It's kind of funny. And so down here, ARR plus n, well, what is that? That is the address of the first element, plus n, that's the address of the nth element. And so, if I had said ARRN, that is dereferencing the thing at the nth element, and if I want to get the address of that thing, I use the address of operator. So these two statements are equivalent as well, okay? This one is faster than this one, because this one does all of this inside of it, right? So you'd just do something like that. So that's just to show you that all of these things are like equivalent. And of course, what is the problem? Just put your hand up instead of just everyone shouting it. What is the problem with this code? Why would you not want to write code and just run this? We've already done an example of this. Why? Exactly, right? So I've allocated something on the heap that I have not freed or deleted. Okay. Again, here is something that I can do. If I allocate a 3-element array on the stack, then all of its values live on the stack. ARR0 equal to 5, I can put that there. ARR1 equal to 10. Or I could say ARR plus 2 and dereference that and set it equal to 20. Okay? Now, even though I have not used the star here, this array, ARR, that's still a pointer. Okay? So just to make things a little bit more complicated, this ARR, whenever you allocate an array, what the variable actually is a pointer. So if you've ever heard somewhere in life that arrays in C are pointers, that's what they're saying, right? The variable is just a pointer, and the pointer is to the first element of the array. Now, all of these arrays, what might be something that's super annoying if I want to go use that array later? What's the difference between an array? Well, one of the differences in terms of usability in this array in C++ or C and an array in, say, Java or a list in Python. Well, let's put a hand up. Yeah, go ahead in the back. Okay, yeah. So first, we can't change the size because this is a statically allocated array. The next thing that I was actually thinking of, but that's a really good point, is let's say later on, I want to iterate through this array. What would that for loop look like? What's the stopping condition of that for loop? So someone different, if you write a for loop, what is the stopping condition of your for loop? Just put a hand up, please, because I don't know where. Yep.
The size of the array.
The size of the array. How do I know the size of that array? It's 3, but that's not stored anywhere as a variable. Okay? So one of the annoying things about arrays, raw arrays like this on the stack or on the heap, is that you don't know what the size is. So you can't just loop through it, right? So that's a little bit annoying. So what we would have to do if we wanted to record the size of arrays is make some sort of data structure around an array, like a class, right? that would also store the size that we had allocated for that array, so then we could know how big it was when we went to do things. So C and C++ don't do anything extra for you, right? One of my favorite quotes of all time is that the problem with computers is they only do what you tell them, not what you want them to do, right? And this is doing what you're telling it. Give me space for 3 things and return the pointer. Doesn't tell you how big it is after that. Okay. Why would we want to use pointers then if they are so dangerous and expensive? Well, there's several reasons. One, and these aren't in order, okay? Pointers must be used for inheritance. So in other languages, like Java, for example, Java just uses pointers behind the scenes. It calls it a reference, but it's really a pointer. It's actually like a copy of a reference or something, but it's essentially a pointer. So in C++, whenever we want to say, hey, my base class pointer, my base class variable is equal to a derived class, we can't just say base b equals derived. We can't do that. Why? Because everything that we allocate on the stack, right, this base may be of a different size than the derived class. So my base class may be 8 bytes. My derived class might be 40 bytes. And so if I'm allocating 8 bytes for a base, I can't then go and set it to derived. Okay? So the way that it gets around this is that by using pointers, because the pointer is always going to be 8 bytes, 64 bits on a 64-bit machine. And so it says, give me a pointer to a base class, but it's actually a derived class instance of that. Okay? And one of the other fun things that we'll learn later is that there's no reflection in C++. So it's kind of difficult. Like, you cannot just be given the derived type from a base class pointer. So once I have this pointer down the road, the only way for me to know what that derived class actually is to check to see if it's a particular derived class by casting it. And if the result of that cast is not 0, then it's actually that thing. So I can't just ask it what's the type of that thing. So that's a kind of annoying thing about C++. Also, we would use pointers because of pass by value versus pass by reference. So for example, if we ever want to modify something that we have passed into a function, we would have to use pointers for that. Or also pointing to large data, right? So if we have a large amount of data, you're doing some big machine learning thing and you got to load a gigabyte from a file, you certainly can't put that on the stack. So these are 3 main reasons why we would want to use pointers. References also exist in C++, just to make it even a little bit more complicated. And references are essentially what they call safe pointers. They're kind of also just as dangerous, but it's harder to be dangerous with them. So instead of a star, we use an ampersand. Yay, another friggin' overloaded thing. We've seen this before. It meant dereference, but now it means reference, right? It means the same thing. Flammable means inflammable. Okay, so a reference must point to existing data and can never point to nothing or a null pointer. So back in my example where I said int star p, I cannot do that with a reference. I cannot say int ref r. I have to assign it an initial value, and that's why it's a little bit more safe. This makes them almost always safe. You are still able to do unsafe things. So we want to prefer using references to pointers wherever possible. So if I ever tell myself, hey, I need to use a pointer here, then we would prefer to use a reference instead of that pointer if possible. So by default, anything you pass into a function in C++ is passed by value, meaning that it is going to create a copy of that thing, and then that copy is what lives in the function. So pass by value has a cost for copying a large amount of data. Also, we may want to modify the value that we passed. And so if we pass in a copy and then we modify the copy, when that function is done, it destructs that local copy and we haven't made any changes to the thing outside that function. So we can use pointers to accomplish pass by reference, but ideally we want to use references wherever possible. Now again, There are people out there who are like hardcore C++ enthusiasts that would never touch a reference because they're super duper programmers and they would never make a mistake, and so they just use pointers. In a lot of libraries, you won't see them use references, they'll use pointers, because what's the point of using references if they could possibly still be unsafe, etc., etc. But in order to be good, students, we're going to use references wherever possible because they are safer and technically they are preferred. So let's say we have this function, tenify, which takes something in and changes it to 10. What a great function. So in our main function, we have int I equals 12. We call tenify on I. Hand up, please, not shout it out. What will be printed by this? Yep. 12. Why?
Since it's passed by value, the I main function doesn't.
Exactly. Right? So this is int A. The integer is going to be copied. So we have one integer down here on the stack. Then we're going to have a completely separate integer on the stack up here, which we're going to set the value of and then return and just pop it off the stack. And so the cool thing is, if you had a smart compiler, which we all do, I think if you pass this into an optimizing compiler, which all modern compilers are, if you tell them to optimize, this call to tenify and the code for tenify would probably just be deleted. Like, it wouldn't happen. It wouldn't call that function because it would know nothing happens here. By definition, nothing happens. It can't do anything. I've made a copy, I've modified the copy, I've destroyed the copy. Literally nothing can ever come of this function. Okay, let's look at this function. Still tenify, but now we take in a pointer to an integer. That pointer then gets dereferenced and changed. So down here we say int I equals 12. Since we have to pass in a pointer or an address, we can no longer just pass in I. It will be a compiler error, because if you pass in I, you're passing in a different type than it expects. So we have to get the address of I, pass that in, and now what this says is, okay, believe it or not, this is still passed by value. But what's being passed by value? The address. It's okay to make a copy of an address because it's still the thing that I want to change, right? So it's like me writing down my address and giving you the piece of paper. If you show up at my house, it's still my house, right? So here I've copied the address. So up here there will be a copy of that address on the stack. Now maybe some compiler would optimize that away, I don't know. But it would say, okay, look up the address and change the value at that address to 10. So down here, we would actually tenify I, and that would print out I. But be careful, this pointer may be null. We have not done any error checking here to make sure that we are not dereferencing a null or invalid pointer. Okay? So if you've ever in Windows had a program crash and then the error was like invalid reference at 0x00005 or whatever, for some reason it has a 5 at the end of it, that is the address that's returned by a lot of things that return null, and then your program was trying to dereference it. So hey, oh crap, I've got a null pointer dereferenced somewhere. So in our program, in practice, if we work with pointers, then we have to put in error checking here. So we could put in an assertion that says assert that A is not equal to null pointer, something like that. Pass by reference is another way of doing it, and we would pass in a reference to an integer. Okay? Now, if you look online, some people might put int ampersand instead of int space ampersand. Some other people put int space ampersand A. So like how you do it, the white space doesn't matter here, as long as it's not all one word. Okay? It has to be separated at some point. So here, if this expects a reference, the cool thing about references is we no longer have to get addresses of things. Okay? So I can just pass in I, and the compiler knows, oh, there is a function which either takes in an integer or a reference to an integer. Okay? So this would change the value to 10, and we would get 10 printed out down here. So we prefer using references wherever possible, and we know that reference, unless you've done something crazy, which I have done in the past, and has caused me days of debugging, that will typically be a valid reference, and you won't have to check for null pointers there. Let's say we want to pass some large data, right? And we have some big data, and I want to machine learn on that big data. Well, this is going to copy that big data. I don't want to copy that big data. I want to pass that in by a reference. And additionally, if this is data that we're going to be learning from, pass by reference, that lets me modify stuff, right? Typically, a function like this, I want to be sure that my data is not being modified, right? I'm just learning from it. So wherever we want our data to not be modified, I put const there. This is in a lot of languages, but in C++, with some exceptions, pass by const reference if possible. Okay? Because I'm not copying the whole data, and it's also const, so I know I'm not going to be changing the data. So wherever we pass a variable to a function that we don't want to be modified, use a const reference if possible. Const declares that the variable cannot be modified inside the called function. Now, it's C++, so of course you can do whatever you want. And the really dumb thing is that inside this function, you could just cast this variable as a non-const reference and then modify it. So, but by default, it's just like it's a safety measure, but it doesn't ensure that we're safe. You can always do whatever you want with the bits with C++. Just realize that. Okay. We only have to pass that 8-byte reference. So again, a reference is just a memory address. It'll give you the same thing as a pointer, but the compiler does a little bit of extra checking. And this may be far less data than the data that we're passing into the function, right? So this big data, that could be gigabytes, but we're only copying the reference, which is an 8-byte thing. All right, exceptions to pass by reference. Pass primitive data types by value. Always. I had a program once that I had so many functions in this program, if you did 3200 with me, it was a search program, okay? And it was a heuristic search program, and everywhere in the code I had been told pass by const reference all the time. So I did. Like a good little boy, I passed by const reference. And then someone looked at my code and they're like, why are you passing integers by const reference? I'm like, because I was told to. And then they were like, well, do you understand what's happening here? You're taking the integer, you're calling the address of operator, you're passing the address into this thing, and then in order to get at the value, you're dereferencing the address that you just got the address of, and then you're copying that address into here, right? So it's non-trivial, but here you're just copying A, right? So if you don't want to modify the thing, don't get references involved if it's a small piece of data. So if my piece of data is of less than or equal size to a memory address, just pass that thing, unless I have to pass it by reference by some reason. Now, some people would say, why are you passing int A? If that's a copy, why bother putting the const thing there? Right? Because if this is a copy, well, you never have to worry about the original thing being modified, but I would argue that you still, if you don't want that A to be modified, let's say inside that function, on the first line, you do something with A, and then maybe on the 10th line, you do something else with A. If I don't want A to be modified at any point in that function, this const will still protect that from being modified, right? So if I do pass in an A, let's say that's some option, like, I don't know, the number of monitors that I have, or whatever the resolution might have to be. If it's not const, then inside that function, something could modify A by accident, and then I could use that value of A that has been modified. So even though that this is a copy, the const keyword still does something here. And so this referencing and dereferencing is kind of an extra computational step, and so what happened was I changed all of my this into this, and my program ran like 15% faster. It was insane. And now you're not going to see that level of speed up in practice, but my program had so many of these function calls that's where one of the bottlenecks was. So referencing has an extra dereferencing step, which is slower when using primitives, so just pass primitives by value. And what we're going to see is this thing called a shared pointer, which we're going to be using extensively in the course, which is a smart pointer, which I'll get into in a second. You're going to pass shared pointers by value, because the copying of the shared pointer actually has some context, which is important. So I'll get into that in a second. So C++, memory management, pointers, all this nonsense, oh my god, it's a lot to deal with, I understand. But luckily, we have this concept called RAII. Resource acquisition is initialization. Worst name ever, but it's a good concept. And what it does, in technical speak, is it binds the life cycle of a resource that must be acquired before use to the lifetime of an object. Okay? So, it makes life easier by implementing things in a way that automatically manage memory and resources within an object. So, what we're going to do in order to implement RAII is encapsulate each resource into a class, and then the class constructor is going to acquire the resource and initialize it. So in the constructor, we're going to call new, and then in the destructor, we're going to release the resource. So we're going to call delete. And so the class itself should be instantiated such that it either has automatic storage duration, meaning it's stack allocated, or it's within another RAII object. So as long as our chain of object storage is all RAII, we never have to manage our own memory again. So let's have a look at this, for example. Let's say I want to have an RAII for a raw integer array, right? So we saw the dangers of using int star array in our code because we may forget to delete it, right? So what we're going to do is we're going to create a class called intArray. Then in the constructor, I'm going to have as a parameter the size of the array that I want to create. Then I'm going to have array equals new int size. That will go to the heap, return the address, and then set the address here. Then I'm going to have an operator here, which, so C++ has operator overloading, where I can actually define the square bracket operator. So now I can say array I, like this, outside the class. So my custom class can have square bracket operators. It's really cool. But the important thing here is that inside my destructor, so the destructor is the tilde version of the constructor. It's basically not, so it's the opposite of the constructor. That's why it's tilde. I delete that array. So the syntax for deleting an array in C++ is delete bracket bracket array, where if it was just a variable, you just called delete array. And what this does, delete bracket bracket array, it says, hey, that thing is an array, and so if we're deleting an array, it will actually go through that array and call delete on everything in that array. Okay, so that's the way we do this. Then we can do something like this. Int array, array, 10, inside the constructor, the memory is allocated. Then I can do whatever I want with that array. And then down here, since this array object is stack allocated, it gets popped off of the stack. And when an object gets popped off of the stack, its destructor gets called. And so when the destructor gets called, the memory is deleted. Cool. So as long as we deal with the memory on a case-by-case basis in our RAII objects, we can just do this in C++ and never have to worry about raw pointers, about allocation, about worrying about memory. It's just all done for us by our smart object. Now, we're talking about pointers. There's something that comes with C++ which is very convenient, called a smart pointer. So let's say we did want to have a pointer to our big data, right? Our big machine learning data. So our big data pointer, okay, now we've got to create what? I've got to have I've got to create a class for that big data pointer. Now I've got like a texture. I've got to create a class for wrapping around that texture. I don't want to create classes for every possible case of wanting to do RAII. Luckily, C++ has done something for us. and it's called a smart pointer. So it can be really cumbersome to create our own classes for every single data type that we want to store a pointer to. C++ contains something called smart pointers. In this class, we're going to be using shared pointers. There are different types of smart pointers other than shared pointers, but let's just use shared pointers for now. Once we've used them a bit, I'm going to tell you the difference. And what it does is it completely handles RAII for a given pointer or a given type. So a shared pointer is also called a reference-counted pointer. And this is kind of what happens in garbage-collected languages. It's not exactly the same, but it's sort of what's happening in a way behind the scenes. So let's say we have a class, and we're going to wrap like our big data pointer in a class. So what a shared pointer does is its internal counter is going to be set to 1 in the constructor. And this is a reference-counted pointer. So what this 1 means is that here's the number of scopes of code which can currently access the thing that lives in this pointer. Okay? So every time the shared pointer is copied, so let's say we allocate a shared pointer in our main program, the counter's set to 1, then we pass it into a function by value it's copied, and now its counter is set to 2. Because I could be still accessing this shared pointer in the main function or in the new function. Every time a shared pointer destructs, the reference counter is decreased by 1. And so when the count reaches 0, it knows that nothing could still be accessing this pointer, and so then the heap memory is deallocated. So let's have a look at this. We have our main function down here. In order to use shared pointer, we have to use the memory. We have to include memory. That's where shared pointer lives. So down here, I'm going to create a standard shared pointer that is of type myClass. I'm going to call that P. The constructor of the shared pointer is going to take in a pointer to an object that I want to be reference counted. So I'm going to create a new myClass with my arguments. So this is going to go to the heap, ask for the memory, return the pointer, and then shared pointer is going to be constructed based on that pointer. Okay? So now the count is equal to 1. So one place in my code exists where I could possibly be accessing this pointer. And that is the main program. Now, if I had called func, right, with a shared pointer of my class of P, so if down here I called func with P, then in that function, this object gets this object gets copied because it's passed by value. Whenever you copy a class, its copy constructor gets called. In the copy constructor, it increments that reference count because now not only could something be using it in main, but something could be using it in here. If we then do something to that and then we exit, in the destructor of this copied shared pointer, it decrements that reference count. And now when we get back to here, we know that that reference count is back to 1. And so when this exits, we know that the reference count is 0, and then it deallocates. Okay? Similarly, if we had a vector of shared pointers to things, when we put something into a vector, it copies it. And so if it lives in that vector, then we know something could still be accessing it, so we won't be dereferencing it until that vector gets destroyed. So, also, this is like the old pre-C++ 11 way of doing this. Never actually do that, actually do this. So in C++, if we want to make a shared pointer, I was just showing this for like theoretical purposes. This is how it works. But under the actual syntax is we would say standard make shared. And so it's a much simpler way of doing it. So make shared was going to return a shared pointer of type myClass, and I just pass in the arguments. And instead of having to type standard shared pointer myClass as the type, in C++ we can use the auto keyword. And auto can be used anywhere that we are returning something of a known type. So C++ got smart enough to know that, hey, This is actually a shared pointer to a my class, and so that will just like type it out for you if you put in auto. So that is a shared pointer, and you can use a shared pointer to automatically manage the memory of a pointer for you. And we will be doing that in this course. Now, some people who are very adept at C++ and low-level optimization would cringe at the use of shared pointers. But again, they are a little bit slow because every time you pass your shared pointer into a function, a copy constructor gets called, then a reference counter is called, then when it destructs, a reference counter is checked and then destructed. So there is a non-zero overhead to using a shared pointer. However, the convenience that it will afford us in this class in learning to do what we're going to do is so nice that it's worth the slowdown. At the end of the course, I'm going to show you, hey, here's how we can get rid of shared pointers. Okay? But let's just use them for now because we don't really have that knowledge that we need to be able to throw them away just yet. So these can be used in place of raw pointers to make sure that you never have to delete things later on down the road. And as long as you use them correctly by properly passing them by value instead of reference, then you will never have a memory leak because of a pointer if you use shared pointers. Okay. The rest of this is just some reference material. So this is C++ inheritance. I just included this here. You have public and private and protected. All of you should probably know all of that. So if you want to do inheritance in C++, you would say class derived : public base 99% of the time. I have never ever wanted to create a private or protected derived class. In fact, I don't even know really what that would do. That should have been at the end. I think I misput the slides. Okay, so how to allocate and pass data in C++. Yes, it's a little bit complicated. We have a number of different ways we can do things. This gives us enormous power, but as a wise man once said, with great power comes great responsibility. So if possible, use these rules. Okay, so these are some rules here. If possible, use the stack. If you're just allocating an integer to do something with or to keep track of a count for a second, don't use the heap, use the stack. Pass variables by const reference if their size is greater than 8 bytes, usually a decent rule. If you have like an unsigned long, which is probably 16 bytes, okay, pass primitive types by value. Unless you want to modify them, then you need a pointer or a reference. If you need heap memory, and again, this is for this class, use a smart pointer. Okay? So standard shared pointer to my big data. If we are going to be allocating derived classes and storing those derived classes in base class pointers, then I would say standard shared pointer base equals standard make shared derived. Okay? Now, funnily enough, you're not actually going to be doing a lot of that in the course because most of that kind of thing I'm going to be giving you in the skeleton code for the assignments. So the way the assignment works is I'm going to give you, other than assignment 1, which is a single file, I'm going to give you a bunch of files, and it has like, it does the window management and stuff for you, and then you implement the game mechanics. And so typically, this is going to be done for you behind the scenes, and then later on, our factory that we make is going to be doing all of this stuff for us. It's done for you, but I want you to know this stuff so that when you go out on your own and do your own, these are good rules to follow. And only when absolutely necessary would you use raw pointers or new. And hopefully, this shouldn't happen in this course, and I made the assignments so that it doesn't happen in this course. But if you did, for example, wanted to write your own vector, which has fewer or less functionality than standard vector, right? So I want to write this blazingly fast vector class that can shrink and grow by this exact amount that I know is perfect for me. Then, of course, you would need to use raw pointers, and you would need to use new in order to allocate those arrays that you're going to use. But if you do have to use this, if possible, use RAII, encapsulate that in a class. And the last thing I'll talk about today are templates. We will be using templates in the class, but I will explain those on a case-by-case basis as we come across. But templates are C++'s way of implementing generics. It turns out there's also this thing called template metaprogramming where you can actually like compute things in the compiler, which is absolutely insane. But we won't get into that, but just know that templates can be used to do some crazy stuff. They're extremely powerful and easy to use. They can be very complicated if done incorrectly. We will keep it very, very simple in this course, and we will only be using C++ templates to implement generics. So for example, a generic would be, hey, I want to have a vector class, but I want it to be able to store any type. Right? So ints or floats or doubles or whatever, and the way I would do that is using generics. And I believe in the live coding section after this that will be in the video, I do an example of C++ template. So what we want to be able to do is have a data type or a custom class that depends somehow on a data type. Like here, I would want a standard vector of type t that stores of type t. And I say, let's just do a coding example, and now I'll snap my fingers, and we're into the coding example. But that's post-production magic. So, all right. Any questions before we get into the live coding? Any questions about any of this stuff? Yep.
Is there a standard way to declare copy constructor, just as destructor?
Yep. So in your class, you will have your constructor, and you can have multiple different constructors. So for example, in your class, I can declare a default constructor, which has no arguments. And so this would just be, if I said my class C with no arguments, that would be what was called. I could also, let's say if I have a vector, one of the things you can do with a vector is set it to an initial size with some elements in it. So a constructor can take arguments. Maybe we would want to have, 4 number 100s in this vector when it's constructed. Another example would be if I want to take in like a file name for a constructor, I could pass in a file name for a constructor. If you declare a constructor that has a reference to the same object type as that class as the parameter, then that is what will get called as the copy constructor. I believe so. If you want more details on that, if you just Google C++ copy constructor syntax, you'll get the CPP reference complete details. But yes, in your class, if your class is plain old data, meaning it's just base types that live on the stack, then your class, the default way to copy a class is just by copying everything. But if your class, for example, contains a raw pointer somewhere, and you copy it that way, then it's just a shallow copy. Have you all heard of shallow copy versus deep copy? Okay, so some of you have. So a shallow copy would just be copying the pointer, but probably what you want to do there is create a new pointer and copy all the data from the old pointer into the new pointer so that you have a true copy. So that's the type of thing that you would do in a copy constructor. And if you copy a vector, for example, that's the thing you would want to do. You wouldn't want to have it so that modifying the copy of the vector modified the original vector, right? So, any other questions before we're done? Cool. All right.
So that's the end of the official lecture, and now I'm going to get into some live coding so that I can show you some cool stuff. Alrighty. So let me pull up my notes, and we're going to start doing some live coding. So again, if you're a student in the course and you have another class now, if you're watching live, by all means, you don't have to watch this now, but come back to this. It will be here if you want some more practice with coding C++. Alrighty. So let's open up some code. I've already got my my template code here typed up. So again, we're including IOStream, so I can print some stuff out. I've got my int main, and I've got my return 0, and that's it. So let's do a little bit of practice with all of the stuff that we said. And someone said, can you please show us variables stored on stack are contiguous? Yes, I will. Okay, so let's do that. So first, let me make a variable. So int a equals 10, int b equals 25. So these are stack allocated variables. All right. So what I'm going to do is I'm going to print out a and then a new line. And then I'm going to, oops, I don't have my semicolon. Standard cout b and then a new line. Okay, so I'm gonna compile and run that. I'm gonna hopefully get 10 and 25, and I do. All right, so now what I can do is I'm going to say, let's look at the address of both of these things. So I can print out the address of A, and then a blank, and then the value of A, and I can print out the value of B, or the address of B, and then the value of B. So again, if I use ampersand, that is the address of a variable. That tells us literally the address in RAM where that thing is stored. Okay, so let's look at this. Now, I've got a huge hex number here. That is the address where the variable A is stored. That's it right there. And the value of that is 10. Here, I've got the address where B is stored, right? This is a 64-bit integer because my computer is 64-bit, okay? And it has the value of 25. And if we look here, this address ends in 60, and the very next integer that we allocated is at 64. Since an integer is 4 bytes, well, let me do this too. So what we can do here is I can also print out size of A and size of B. Size of is a function built into C++ that tells us how many bytes does this data structure need in order to be stored. So let's compile that again. Oops, I didn't put a blank in there. Okay, so let's do that. All right, so here, and you can see when I ran it again, it had this is a different memory address, right? Because I ran the program a different time, not guaranteed to be in the same place in memory. But A has the value of 10, it takes 4 bytes, and it lives at this address. B has the value 25, it takes 4 bytes, and it lives at this address. And this address is 20, this address is 24, which is 4 later. So it means that in memory, A is right next to B, exactly how I said it would be in the thing. All right, let's write a function now that does this, because I'm going to probably want to do this a number of times with some different data, but I don't want to have to type that for each time. So let's write a function. So let's say I'm going to write a function. That function is going to be void, right? Because it's just going to print something. I'm going to call that pp for pointer print. I am going to pass in a reference to a variable. Okay. Then I'm essentially going to do this. So let's just copy and paste this up here. Okay. Remove that line, and now what I can do is I can say pp a, and I can say pp b, and that should work. Okay, so I get the exact same thing. Now I have that function that does that for me. Okay. Someone said, shouldn't we pass primitives by value? Yes. However, in this, that is a very good question, and I'm very glad that someone asked that. However, what I'm trying to show you here is the address of this variable, of that A, and the address of this B. If I instead had passed, well, let's just do it and see what happens. If I just pass A into here, A gets copied here. Actually, let me change this to I to make it a different variable name. So we have I, and I. Okay? So if I pass A into here, it will be copied. And then the address of the copy is what will be displayed. You get that? The address of the copy gets displayed. So if I run this now, look, I get the same address for both variables because they're both copied into that function. All right? So yes, this is a different variable. This is not the original A. And because this is the variable that lives at this stack frame whenever we call pp, it's actually going to have the same address. So we want to pass a pointer into it, or a reference into it, or a pointer, so that we actually get the memory address. Okay? All right. So let's look at an array now. All right. So let's say we have int array, and it could be called anything, 10. Okie doke. So int array 10. That's how I do a stack allocated array. Now, let's say that I want to print all of those things. So I'm going to say for size t, I equals 0. We talked about that last time. I less than 10, I plus plus. And now I'm going to call my pointer printer on array I. So what does this do? Oh, wow. Okay. What in the hell is going on here? This is weird. All right. Let's look at the values. 0, 0, negative 119 million, 21,989. 0. What is going on with these values? Well, we didn't give them a value. Remember how I said that in C and C++, it doesn't waste any time. It's so fast, it doesn't even give these values, right? It just says, hey, whatever happens to be in memory at your memory addresses, that's what we're putting here. So in C++, there's a nice shortcut. If you want to give these all default values, which for an int would be a 0, I can just give it this syntax. Okay? So let's do that again. All right. Now they all have values of 0. Let's look at their addresses. So since this is a stack allocated array, it's going to be contiguous in memory, right? So each of these should be 4 bytes away from each other, and they are. C0 plus 4 is C4 plus 4, C8 plus 4, CC plus 4, D0. So we can prove that this is contiguously allocated in memory. Got it? Now, let's do another thing. Let's make a heap array. I'm calling that heap array, and that's got to be a pointer, right? And that's going to be equals new int 10. So I'm going to do the same thing, but I'm going to do that to the heap array. And now I'm going to do the same thing, but let me do it for the heap array. Heap array. All right, perfect. So this up here, this is the stack allocated heap, or the stack allocated array. Down here, printed right after, is the heap allocated array. So you can see here that the address of stuff on the stack is very different than the address of stuff on the heap. Okay, so this starts with like 563. So in my computer, this memory is actually living several gigabytes away from this memory, which is kind of funny, but that's how it is. All right, so this memory, that's the heap allocated memory, and it has a different address than the stack allocated memory because heap and stack are actually quite different. They're quite far apart in memory. All right, so this would actually now be, I did not free that memory, so that was a memory leak. But we're going to get away from doing that anyway, so don't worry. All right, so let's look at pass by reference versus pass by value. like we did before. So those are addresses. Oh, let me do something else here. No, I don't want to do that. Okay. Undo. There we go. All right. Phew. Let's do a little bit more about pointers. Okay. So I'm going to have my int a equals 10. Then I'm going to have int star, which is an integer pointer. Some people put it like this. That's fine. So an integer pointer, that is going to be a pointer to a. And this is going to be equal to the address of a. Okay. Now I'm going to have int b equals 25. And I'm going to have an int pointer to b equals the address of b. So what I do is if I call pp on a and pp on b, I'm going to have the same thing that I had before, right? Looks kind of the same. Now, let me try calling pp on pa. What's going to happen? Oh, it's going to say, I can't do that because here, this is expecting a reference to I, okay? A reference to I, but we're passing in a pointer to an int, not a reference to an int. So that's a mistake. Okay, so now what happens if I say whatever lives at PA, I'm going to change that equal to 17. Now, oops, let me do that first. Now what's going to happen? Well, instead of 10 here, we have 17, right? Because I say whatever happens to be at the pointer, or sorry, at the address that this pointer is pointing to, which it's pointing to A, I'm going to change it to 17. Similarly, what I could have said was whatever, so I'm going to dereference this memory address or this pointer, and whatever happens to live at A, right? Whatever happens to live at A, I'm going to dereference it and make it 17, and that's the exact same thing. So where I had just said star PA equals 17, these two lines are exactly equivalent because up here I had set PA equal to ampersand A, which is the address of A. Okay? So here we go. Now, this is where stuff starts to get interesting. Okay? This is, if you were taking a security course, this is where you would start doing security stuff. We're not going to do this in this course. I just wanted to show you something, why pointers are dangerous. Look at this. So we showed that the variable A lives in memory 4 bytes before the variable B. Okay? Or 1 integer away, essentially. So watch this. I'm going to modify A without ever accessing A or its pointer. So if I wanted to modify B, I could do this, right? So B equals to 17. Oops. Oh, PB, sorry. So this is me modifying what lives at PB, which is the variable B. So now we'll print out 10. Ah, geez. 1 second. Oh yeah, I modified it. Sorry. I modified it before, after it printed. So star PB equals 17. That will modify what is at B. All right. So there we go. So I apologize. This is live. We're going to have a few little mistakes. So now instead of 25, we get 17. Now, just watch. Pointer arithmetic, if I say PB minus 1, what that does is it knows that PB is an integer. Okay? So because it's an integer, if I subtract 1 from it, it's going to subtract the number of bytes that's in A, or sorry, that an integer takes. So since an integer is 4 bytes, this is actually going to be the memory address of B minus 4 bytes. Since A lives at the memory address of B minus 4 bytes, now A gets modified. See that? Isn't that crazy? We've modified the value of A without ever actually explicitly saying so. And so if you modify pointers, you're going to get a whole bunch of stuff that goes crazy. All right? And this is why raw pointers are dangerous, and this is why in this course, this right here is the last time, well, not the last time, but one of the last times you'll ever see a raw pointer. All right. Okay. So what we're going to do now is let's demonstrate. Let's see. What am I going to do? Let's demonstrate RAII by making our own int array class. Okay? So we're going to make a class called int array, and we're going to do what we did in the slides. So this int array is going to encapsulate an array, and I'm going to give that the m underscore Hungarian notation because it's a private member variable. Then public to int array, I want to have int array be a, we're going to take in a size. So this is going to be the size of the array, right? Then I'm going to have a, so let's do that. How do I allocate this? Well, I'm going to say m array equals new int size, right? So if I wanted to make a dynamically sized int array out in the wild, I would have to call this new syntax. But right now we are demonstrating RAII by wrapping this inside a class, okay? Now, the other thing about C++ is that it does not know the size of its arrays because all this is a pointer. It points to the first element of the array, but it doesn't know how far that array goes. So I'm going to have to store that size as well. And that is the size of the array here. All right, so that's the size of the array, and I've got the pointer to the data. So here, as I said before, I talked about initializer lists, so I can say mSize and put size here. And similarly, how I did this line down here, I could even do something like this, where I say mArray and then go new int size. So I can actually do that in the initializer list like this. So let's just leave it. Now let's compile, see if anything complains. Expected qualifier, Oh, I'm not supposed to have this right here. There we go. So now we compile. M size will be initialized as okay. So it's complaining that I declared this variable second, but I'm initializing it first. And some compilers actually complain about that. So let's just put it above, and now we'll recompile, and okay, now we're good. So we're on our way. We have that the constructor acquires the resource. Okay, the constructor acquires the resource. And I'm going to call here, I'm going to say standard cout array constructor. All right, so now we're going to print out whenever we construct the array. Now, how are we going to add things to the array? Right? So let's not do add, but let's just like get and set. So if I want to get something from the array, then I'm going to say int get. I'm going to have an index. And getting from the array will not change the array. So this is going to be const. Remember our const correctness talk. And now we're going to return mArray index. Perfect. So that's how I would get something from this array. Now I want to be able to set something in the array. So I'm going to say void set. In order to set something, I'm going to need an index and an int value, right? This is not const because I am going to be changing things. And what I'm going to do here is I'm going to set the index of that array equal to value. Okay, so now I've got a fully functional dynamic array. I can get things from it, I can set things from it, or set things to it. So down here, let me call int array, and this is going to be called my array, and I'm going to set this up with 10 elements. Okay, now what I'm going to do is I'm going to call my array. Oh, before I do this, let me actually write a function that prints this out. So I'm going to make a function called print. That's going to be const. And then I'm going to say for size t I equals 0, I is less than m size, because that's the size of the array, I plus plus. For all of you C++ nerds out there who say, you know, you should put plus plus I here, that is optimized out by the compiler. So by saying that, you're admitting that you think that matters. So I plus plus is fine here, some plus plus I. Anyway, so we're going to say standard cout. We're going to print out the index, followed by a blank, followed by the value, which is m array I, followed by a new line. Okay, so if I come down here now, and if I just initialize an array, and then I call my array.print, what happens? Okay, so this is all initialized to zeros. Now it turns out that when you say int star whatever equals new int, the new operator in C++ will set it all to zeros for you. Okay, just lost my window. Okie doke. So now let's actually do something to the array. So I'm going to say my array dot set. So I'm going to set in index 4, I'm going to set the value of 7. And in my array dot set, index 2 is going to get the value of 134. And then when I print, look at that. So index 4 has the value of 7. Index 2 has the value of 134. We have, who can tell me what I'm missing? I'm allocating the array, but I am not yet destructing or freeing the array properly. Okay, so the destructor is something that I have to write, and the destructor uses this syntax. It's the same as the constructor, but it has a tilde in front of it. And what I have to do here is I have to call delete and then this. Just a weird syntax, but it says delete whatever's at m array, and it is an actual array. Okay, so that is going to free the memory that I allocated. All right, but down here, look, and in the destructor, I want to do one more thing, which is standard cout array destructor /n, boom, boom. All right, so now if I do this, it calls array constructor because the array was initialized. Then I do some stuff with the array, and then at the very end of the function, the destructor is called and it cleans up everything for us. So look at that. We wrote our own function, or we wrote our own RAII class that wraps around this array. Someone is asking out there, how can I grow the size of the array? You can delete it and reallocate it, or you can call realloc. That's not the point of this lecture, so I'm not going to spend time reallocating or growing things. It's really not the point of this lecture. So I'm not going to answer that. Please just go Google it. So it'll just take too much time. So I apologize that I can't answer your question right now. What was I going to say? So I have this now. I've created this class. But what if I don't want ints stored in here? What if I want to store floats or any other class? Well, what am I going to have to do? I'm going to have to write a float array. I'm going to have to write a myClass array, right? So turns out that just like in Java, we have something called generics. And generics allow me to write one piece of code that does a bunch of different things for us. And so in C++, the way we implement that is called a template. And the way we do it is the following syntax. Template class class T. You can also say template type name T. Okay, so you could say type name here instead of class. So let's just leave it as that. Doesn't matter which one you use. And then in here, wherever I said int, I'm just going to replace with T. And you'll see how this works. So up here, this is no longer an array, than int array. This is like a dynamic array. Okay, so it's no longer just going to store ints. Down here, wherever I had int, I'm going to now store T. So this class is written to be usable by any type, and that type is just represented by this T. Okay, so if I come down here, this is going to change to a T. Down here, when I return something, that is going to change to a T get, right? Down here, when I set a value, this is going to be a T value. And when I print, this is okay. So now what I have to do is it's no longer called an int array. It's called a dynamic array. And this dynamic array now needs to take a template argument to tell it what type I want it to be. Okay, so this is going to be a dynamic array of ints. Hopefully I didn't make any errors. Oh my God, I did make errors. All right, so where did I make my errors? Thank you, templates. All right, so let's see. I've got some, oh, I know. I didn't change the name of my constructor or destructor. So constructor and destructor have to be the same name as the class. And I left those as int array. Let's see if this works. All right, perfect. Now I have my array, I have all the same stuff, but I could do it with floats as well. So let me just show you an example here. So if I set this value to like 7.14 and this 134.420, right? So these are float values that are going to be stored as ints. So when I go to print those values, it's actually printing out the integer concatenation of those things, right? So it's a float to int conversion. So if I actually do want to store floats, then what I can do here is just change this to float, and now I'm storing floats so that when I go to print it, the actual float values are there. Okay, see how that works? So this is RAII. You can see down here, I've got a dynamic array, I'm setting values, I'm getting values, and I don't need to worry about memory. There's no worry about memory in this code. And we are going to do this for everything in our game, so we never need to worry about memory. One other thing that I wanted to show you is that if this is a dynamic array, right? Well, saying like get and set, that's such a Java way of doing things. This is an array. I want to be able to say like my array 3 equals 20, right? If it's array, I want to be able to say that. And the cool thing about C++ is we can do that. And I'll show you how. So here we have something called operator overloading. So operator overloading, what in the hell is that? I can create a number of different operators on this class that I can use in any way that I want. And the cool thing is, one of those operators is the square bracket operator. So I can say operator square bracket, and then give it an argument, which is the thing that goes inside the square bracket, and this is going to be an index. And so I'm going to want to call the square bracket operator via index, okay? So that's what I'm going to do. What is the type of this? Well, I'm going to return a reference to a T. And the reason I'm returning a reference to a T, I'm going to show you in a second. But all I have to do in here is return marray index. Okay? So marray index is going to be returned. So down here, instead of setting things, I can do the following. Now I've got a float array here. So I'm going to say my array 3 equals 3.14159, and my array 2 equals 2.78. Okay? Now, what happens when I actually call this? So this here is going to call the bracket operator of my class, which takes in an index, and it's going to return marray index. Up here, it's returning a reference to that memory, right? So this is a reference to what lives at the third index of the array. So what will happen is that will actually change what's in the array. Okay, you see how that works? But if I had just said this, T operator, then what gets returned is a copy, okay? And it actually doesn't let me do it because I'm trying to set a copy of something. But essentially this would, that would be setting a copy of something. It wouldn't actually change the array. So here is what we do, and now we are able to use this just like a normal array without having to call .get and .set. Isn't that convenient? It's pretty cool. Now, it turns out, what if I had something like this? All right. What if I had a const dynamic array? Well, I'm going to print that out. That's fine. The const dynamic array means that this array should never be modified. Okay? But let's say that I want to just print, I want to print my array 2. So, if this is const, and I just want to print something, well, that's fine, right? I'm not modifying it. I just want to do that. So, all right. Just for, I'm not trying to be rude whatsoever. And I'm very appreciative that people are following along in the chat. But every time I say something, you don't need to like tell me what I'm about to do. I'm trying to monitor the chat in real time for questions. So if you just keep typing, like it's a little bit distracting if you're just saying what I'm about to do. So try and just leave it. I appreciate the following along. It's amazing. It's nice to see someone awake out there. But I'm trying to monitor for like questions. So if you have a question, that's great. But if I say something like, well, how will I do this? The spoiler is that I know how to do it, right? So I'll specifically ask the chat when I want to type stuff. But you're absolutely right, is that, let me just show you what happens. This again is running into something called const correctness, okay? So what's happening here? Why did it give me an error? Well, it's because I am calling this operator on the my array, okay? See this? If this is const, then this function also has to be const. So up here, I have to say that this function is const. Now, let me run it again. Now it works, okay? So, yeah, and I could put a const in front of this as well, and that would allow me to print those out. Oops, with no type. Oops, const t. So what this does is it allows me to get access to see the values of this array in a const way, and I know that I'm going to be returning a const reference to that thing as well. So let's do this, and now I print out that 0. But watch now. If I try to use that function to modify the array, my array 2 equals 17, right? And let's say, okay, now we don't have a const array anymore. I know this is going a little bit into the weeds, but I'm just showing you more const correctness. So down here, if I have an array and I want to modify it, Well, I can no longer use this function, okay? The reason I can't use that function is because it's returning a const reference. So this is saying that the reference that it's returning is const. I can let you see the data, but I don't want you to change the data. And so what you have to do is, if you want to be able to both change the data and see const data, is you sort of had to have two versions of this function, okay? So t star operator here, size t index, and then I can say return m array index. So the cool thing about this is that if I do something like this, standard cout my array 2. So what's happening here? I know this was a whole lot to take in, but we'll go over it again. I have my class, which I've declared here. It's an array of size 10. I'm going to be setting something in the array using the square bracket operator. And then I'm going to be getting access to the data as well using the square bracket operator. And C++ allows me to have both of these functions so that whenever it sees that I'm trying to set data, it's going to use the non-const version. And whenever it sees that I'm trying to get data, it's going to use the const version. And it turns out that using const functions allows the compiler to do some nice little optimizations. And so whenever you do something like you have your own data structure and you want to write the operator overloading, make sure you have the const and the non-const versions of the operator overloading. And then we run it and it works perfectly. Okay, so in that amount of time, we've gone over pointers. You know what pointers are. You know what pass by reference and pass by value is. You know what RAII is. You know how memory works now in C++. You know what templates are in C++. You've created your own templated class. And you know about operator overloading in C++ as well. And so this is almost all of the knowledge that we will need to go forward in this course and create some badass games. We are going to create our own whole 2D game engine from this, and it's going to be really fun.